My name is Christopher Herman. I am a graduate student in the Electrical and Computer Engineering Department at Utah State University. This is our presentation for our ECE 6930 Electric Vehicle Design Lab course taught by Dr. Zelko Pantage at Utah State University. My co-lab partner, Tarak Saha, is holding the camera and he will be speaking later. The objectives for this course were to design and build a power converter for an electric vehicle. As part of that, we were to design a boost converter, a three-phase inverter for a BLDC electric motor, and construct a PCB for those components. So, this is our electric bike and our built converter.
Hi, I'm Tarak. I'll briefly explain you the overall system topology of our power converter. So as you can see, this is our physical system. We have a battery, which is a lithium ion battery, 8 cell, each 9 ampere hour, and the battery voltage has a range of 18.4 volt to 30 volt with a nominal value of 24 volt. So from our battery, we can use a DC-DC boost converter to boost it to a 50 volt regulated voltage, and then from there we run a three-phase inverter to drive our motor. The motor is a three-phase BLDC motor which can operate from 36 volt to 72 volt, and which has a current rating of 10 ampere for each phase. And as part of control, we have a PWM controller controlling the boost output voltage, and we have a three-phase PWM controller for the MOSFETs in the three-phase inverter. And we have position feedback going to the three-phase PWM controller, which is basically the Hall sensors mounted on this motor, which gives you the phase information changing in each 30-degree resolution. And we have another microcontroller system which takes rider inputs. We will be explaining this, what are these inputs, and then does some filtering and little bit of control to give particular voltage reference to my boost converter, as well as a current reference for this motor. This inverter takes the motor current each phase as a feedback and runs a hysteresis based control, which controls the motor current based on my rider input. Then, as a part of controller structure for the boost converter, we have a dual loop control, the inner loop being a current loop which senses the inductor average current, and the outer loop has a voltage control based on the bus voltage, which has to be regulated at 50 volt. It takes the feedback and controls with a specified reference given from the filtering and control section. And now the output of the voltage loop is a current reference, and when the current feedback is compared to the current reference with a PI controller, it generates a particular duty ratio, and we have a PWM chip which generates the gate pulses required for these MOSFETs, the half bridge MOSFETs of the boost converter. And it also has a dead time circuit implemented so that we do not turn on these two MOSFETs together, so that the bus voltage doesn't get shorted through this MOSFET. And on the inverter side, it's a simple three-phase inverter, and we have a logic circuit based on the Hall sensor feedback from the motor and the current from each phase. So we are doing a hysteresis control which controls the current within a specific band, and for this project we have chosen a 2 ampere peak to peak ripple in the hysteresis control, and based on the from the Hall sensor pulses, it generates the corresponding required pulses for each of the switches. So this part of the circuit has the gate driver and the dead time implemented to run all 6 MOSFETs. And the converter is rated for 250 watt continuous, but it can go 500 watt peak, which is required during acceleration when you start from 0 speed, or you want to accelerate a little faster when you want to change your speed from a lower value to higher value. And then we come back to the board again. I'll show you the different sections of the board. So we have the battery input coming through this power interface board, where we have fuse for protection, and the battery voltage after passing through the fuse comes to our input side of the converter. And from the input battery voltage we have an auxiliary power supply which generates 5 volt and 12 volt to bias the control circuit of the entire board. And then from the battery voltage through a current sensor, a boost inductor and half bridge MOSFETs, and this is my output capacitor of the boost. So basically from 24 volt battery input through this converter it generates a 50 volt output, and then from 50 volt output we run this 3-phase inverter to get the appropriate voltage for each of the phases on the 3-phase motor. And as you can see, this 3-phase output from the inverter goes through a fuse for protection, through this Anderson connector goes back to my motor. And we have a few inputs coming from the user, which are like throttle, then brake, and the hall sensor pulses from the motor coming to our board for purpose of control through this connector. So in terms of layout, we have the voltage loop and the current loop controller, which is built in with analog op-amps or analog ICs, which gives you a particular duty ratio reference, and through this PWM chip and the gate driver it drives these two MOSFETs. And similarly for the inverter we have this logic circuit, digital circuits and hysteresis comparator, and through this inverter gate driver all the pulses drives these 6 MOSFETs. In this section we have a Arduino Leonardo microcontroller, which basically takes all your user inputs and gives you a particular reference value for your boost output voltage as well as your motor current. And as part of active protections we have boost output over voltage protection, then boost inductor over current protection in both positive direction and negative direction. This is a bidirectional converter. We'll explain you why it is bidirectional later. And then we have additional passive protection, like for limiting the inrush current we have NTCs at the input, so that when you turn on your battery it will draw a certain amount of inrush current to charge up these capacitors. So to limit that we have NTCs at the front end, and at the output we have TVS diode to limit our boost output voltage in case the regenerative power is too high, so that the boost cannot regulate the 50 volt at this output. So we have a energy absorbing TVS and MOV on the boost output voltage, so it can protect to have the capacitor voltage going very high during the regenerative braking. And I think we are pretty much done explaining the converter here, and then I'll hand over to Chris who will explain you the system, how the bicycle input comes, or what all bicycle input comes to our board and what it does.
So here is our hub 3-phase BLDC motor. Internal to the hub there are 3 hall sensors mounted. These are the cables coming from them, the sensor pulses. We have them coming up through here into our board, so we have them as feedback. We also have user interface via a throttle, a button, a 3-position switch, and a brake lever. So the throttle, how we get that is we supply a 5 volt to the throttle. In turn, when we turn it, we receive a voltage back. We take that analog signal into our microcontroller under here, and we map that to our current reference for our motor. The push button here we use as our braking signal, and this brake lever here we use to disable our inverter. The 3-position switch allows us to enable the boost and enable the inverter, or disable and disable. In position 1, the boost and the inverter are disabled. In position 2, the boost is enabled and the inverter is disabled. In position 3, both the inverter and the boost are enabled, therefore allowing you to operate. So now I would like to demonstrate the operation of our bicycle. I will put it in everything disabled mode. So here we have a key for the battery. Turn the battery on. The LEDs show that the Arduino has booted. Power to the board is good. Now I will demonstrate the operation of the bicycle by turning on our boost, then turning on our inverter so we can fully operate. And now I will turn the throttle to provide a reference, and bike moves. Now we can disable the inverter. You'll hear the sound is gone from driving the motor, and we can brake it. And that's it, and we can drive it again. And I can disable the inverter, disable the boost, and turn off the battery.
As you can also see, the chains are removed from the bike so that there is no mechanical power given to this bicycle. It's running only from the battery power. So it's a whole electric bike. Thank you for watching this video. This is Tarak and Chris signing off. Have a good day.
So for the first step in operation is to turn the battery on. Battery won't turn on without the key. Now the battery's activated. We can turn the boost on now by putting position 2, and then we turn the inverter on by putting in position 3. Now everything's good to go, and I can accelerate by pulling the throttle, which I'll do now. And I can ride. And brake. And I can ride again.
Right. So that's I completely understand that's a bad way to do it.
I can break.
Yeah. Right. So that's what you said. I'm not using that stuff for you.
And turn it off.
Yeah.